Thank you very much. Thank you very much for the organizers. So the title was quite the mouthful. Let me start the talk by introducing you to the very interesting phenomenon of distractor intrusions. Imagine that you're looking at the screen and you see a stream of letters and digits flashing one after the other. Your task is to detect and report the digit inside the square. So letters are completely irrelevant. Many studies have shown that we're surprisingly good at attending and reporting this kind of target, even at very high speed. In this case, in a study from our lab, each frame appears for 50 milliseconds, yet accuracy is about 80%. So when attention is directed in the right time, we can encode the relevant information. However, all it takes to ruin this high accuracy is to change one small detail. If you change the stimulus that follows the target from a letter to a digit, accuracy drops from 80% to about 40%. And why? Because the rest of the time, people report seeing the wrong digit inside the square. So this phenomenon is called distractor intrusions, because the irrelevant distractor intrudes into our consciousness. Of course, that also means that it was accidentally encoded in working memory, even though it was irrelevant. How can we explain this finding? Well, an important but often neglected fact about attention is that it's not an all or none phenomenon. It's a dynamic response that develops over time. And importantly for us, it lingers even after the target disappears. This was first suggested by Reeves and Sperling, who described attention using this plot, where the y-axis is amplification and the x-axis is time. They suggested that following a target or a cue, attention behaves like this: a transient attentional response that quickly reaches a peak and then dissipates. The period of time between the onset and the offset of attention can be referred to as an attentional episode. Surprisingly, only a few models adopted this perspective. But for us, this is crucial, as it explains why the distractor is encoded even though it appears after the target. It's simply shared in the same attentional episode as the target. Now, this alone cannot explain why the target is seen on some trials and the distractor in others. So our first contribution to understanding the phenomenon of distractor intrusions is to try to elaborate on its relationship with the speed of attentional episodes. Specifically, we measured the N2PC, which is an EEG correlate of the onset of attentional episodes, that is, the beginning of the attentional response. Now, I don't have enough time to really go over this study, but suffice to say that our main finding is that trials with distractor intrusions were associated with a later latency of the N2PC. This suggests that distractor intrusions occur because there's some variability in the speed of attention. When attention is fast, we detect the target. But in the cases when the attentional episode is triggered late, the distractor gets more enhancement than the target, making it more likely to be selected for report. So this is all the time I have to talk about this finding, but if you're interested, the article is now online. The main question we wanted to ask following that study was, what happened to the target? That is, on trials where participants reported the distractor, what was the fate of the target? One option is that the target was encoded in working memory, but was not reported. So even though both items were encoded, the distractor was mistaken to be the target. The other option is a bit more radical, as it suggests that the target did not gain access to working memory. So in other words, one account suggests that a competition between a target and a distractor occurs only at a post-encoding stage, and the other suggests that the competition prevents the target from gaining access to working memory. How do we go about differentiating between the two accounts? In the first experiment, we simply allowed participants to have two guesses regarding the identity of the target instead of one. We assumed that if both items are encoded, then there should be some uncertainty regarding which one of them was the target. So in that case, if participants first reported the distractor, they should then use the second response to report the target. For the first response, we can see that the behavioral results replicate, meaning that accuracy is much higher in the baseline condition relative to when the target is followed by a digit. Next, we examined the second responses. Specifically, we focused on trials where the first response was already a distractor intrusion. Our main question is, what is the likelihood that the target is reported as a second response on these trials? So what are the options? In the worst case scenario, if the distractor's encoding and the target's encoding are mutually exclusive, then participants should have no information about the target on distractor intrusion trials, and accuracy should therefore be at chance levels. What is the best case scenario? Well, we wouldn't expect 100% correct responses, so reasonable comparison is that accuracy in the second response will match the accuracy in the baseline condition. If participants generally can encode both items, this should be their accuracy level. What do you think happened? Well, it was in between. Higher than chance, but far lower than the best case scenario. That means that we fluctuate between one item and two items, and also suggests that the competition between the target and distractor reduces the likelihood that the target will be encoded. In a second experiment, we ask, perhaps the target is encoded in working memory, but is blocked from conscious perception. So how do we test that? First, the response possibilities were limited to 4 at a time. If you remember, in the original example, the target was 4 and the distractor was 9. So in this kind of response screen, the distractor was one of the possible responses. As such, the accuracy results replicate. In the second kind of response screen, the distractor was not a possible option, so it was unavailable. Importantly, this only occurs after the stream ended, so it did not affect the stream itself. So what should we expect in this case? Well, if the target is encoded on the distractor intrusion trials, then participants should be better able to choose the target now because the distractor will not confuse them. What do you think happened? If you guessed in the middle, you were correct. Better than the worst case scenario, lower than the best case scenario. Next, we also measured participants' confidence. On each trial, they were asked, how confident are they in their response from complete guess to full confidence? Here, we also measured confidence on non-intrusion error trials, so trials where participants were neither correct nor making a distractor intrusion. Unsurprisingly, when participants were correct, they were fairly confident, and when they were making a guess, they were not very confident. And when they committed distractor intrusions, they were pretty confident. So distractor intrusions really are strong perceptual illusions. The last thing I want to show you from this experiment is accuracy on guess trials. So these are only trials where participants said that they were guessing. They gave a 0 confidence rating in their response. When the target was followed by a letter, guess trials had very low accuracy. This is not surprising. This just means that confidence was correctly calibrated with the perceptual information that participants had, or in this case, didn't have, about the target. The main question is about unavailable distractors. If the target is encoded in working memory on distractor intrusion trials, but is blocked from conscious perception, then participants should have higher accuracy on these trials. That is because they will be primed to choose the target even though they are not aware of its encoding. However, that was not the case. As you can see, there was no difference between the two trial types, and Bayes factor analysis showed support for the null hypothesis. So once again, we get evidence that the target was not encoded in working memory. In the third and final experiment, we asked the following. Perhaps the target is encoded in working memory, but is then dropped from working memory because it is deemed to be irrelevant. To answer that, we once again measured event-related potentials and once again allowed participants to give 2 guesses about the target's identity. So first, let's look at 2-item trials, that is, trials where participants reported both the target and the distractor in whichever order. So this is the average waveform. In the 200 to 300 millisecond window, we can see the M2PC. But more important is this later amplitude. This is called the CDA. And why it's important here is because that the CDA amplitude gets larger the more items are encoded in working memory. So now we can ask, what should we expect from the CDA on single item trials? That is, trials where either the target or the distractor were reported. Here are the options. If, for whatever reason, both items were encoded in working memory but could not be reported, then we should expect the same CDA amplitude on single item trials as two item trials. A second option, what if both items were initially encoded, but then one of them was dropped before the response stage? Participants are only looking for one item, so maybe the other was deemed to be irrelevant. In that case, the CDA amplitude should be the same early on, indicating encoding, but then split into two later, indicating that the item was dropped. Finally, third option, if one item is blocked from entering working memory, then we should observe a difference in the CDA from the earliest time window. And what do you think happened? First of all, it's clear that the amplitude of the CDA is different overall. So that canceled out the first option because it shows that the number of items in single item trials was indeed lower than two item trials. Second, if we look at the earliest time window between 400 and 500 milliseconds, we can already see a difference in the CDA amplitude. So this suggests against the idea that both items were initially encoded, leaving us with option number 3. Meaning that on some trials the item was blocked from entering working memory, and that this competition was resolved early on. To summarize, in 3 experiments we found that attending a target does not ensure that it will be reported. When a distractor appears in the same attentional episode as the target, it can take its place in working memory and prevent it from ever being encoded. I want to thank my lab, my mentor, the British Academy, and thank you for listening.